Teton Pass on Wyoming Highway 22 on the western side of Jackson, Wyoming, is a steep road with a 10% grade. A recreational vehicle enthusiast creates a table to guide himself and fellow travelers along this treacherous road. Use either finite differences or average rates of change to generate a function model d of s for stopping distance of a recreational vehicle when moving at speed 10 times s along Teton Pass on Wyoming Highway 22. Then use the function model to predict an RV stopping distance at a speed of 55 miles per hour along Wyoming Highway 22 at Teton Pass and determine its reasonableness. Okay, so they tell us here that d of s is going to be for the stopping distance, and so that will be our variable there. And then s, it's actually not speed. It says here that, the vehicle moves at a speed 10 times s. And so we know that speed equals 10 times s. And so then s is actually equal to speed divided by 10, because to get s alone there, we would just divide by 10 on each side. And so then to actually find the independent variable, which would then be s, then we would just take each of these speeds and divide by 10. So 0 divided by 10 is just 0, 10 divided by 10 is 1, 20 divided by 10 is 2, and so on. And so now we can go ahead and look at our table and just note that, all of the s values are increasing. Also, the stopping distance, d of s, is also increasing. Let's just go ahead and do average rate of change. And so to do average rate of change, since both numbers are increasing the whole time, then we can go ahead and just use that whole interval. So s then would need to be at least 0 here, so greater than or equal to 0. And then to find the average rate of change, we'll take the last minus first dependent variables divided by the last minus first independent. So we'll have 409 18/10 minus 0 divided by 7 minus 0. So that just gives us 409 18/10 divided by 7, which gives us 58, and then a pretty long decimal. We'll just go ahead and round it off to the nearest hundredth, so it gives us 0.4542. So then we would just round that to 45 hundredths. So then our function will be d of s equals 58 and 45 hundredths s, and plus our y-intercept. And so when s is 0, then d of s is 0. And so we actually, that would just be plus 0. We don't need to put that at the end, and so this is our function. And so now to use finite changes, then we need to go ahead and find the differences between all of the s values and d of s values. So notice here for our s values that each one just changes by 1, so we know that delta s will be 1. And so taking the biggest y value minus the next y value, then we get 108 and 56 hundredths. Taking the next pair and subtracting 208 and 76 hundredths from 300 and 62 hundredths, we get 91 and 86 hundredths. And so we'll just go ahead and subtract each of these pairs all the way down. And so we can see that the first differences are all really different. And so it's not going to be a linear function here. Let's go ahead and find the second differences, subtracting each pair again, starting with the largest and subtracting the next number to see what our second differences will be. So 108 and 56 hundredths minus 91 and 86 hundredths is 16 and 7/10. And then we'll go ahead and do the rest here. Okay, and so we see for our second difference, we actually have very similar values. It's almost 16 and 7/10 for every single one with slight variances. And so let's find the average second difference there by adding these 6 numbers together. And then we'll have to divide by 6 to get the average. So they add to 121 hundredths, and then dividing by 6, then we get a fairly long decimal, so 16.7016 repeating. And so we can even round that to 16 and 702 thousandths. And so since these second differences are the ones that are the same, this will be a quadratic function. And so let's use our rules that we know. So we know that 2a will equal the second difference, so let's just round that to 702 thousandths. And then to solve there, we divide by 2 on each side. And so we get a equals 8 and 351 thousandths. And then we also know that a plus b will equal the first difference between s equals 0 and s equals 1. And so in that case, that's 8 and 35 hundredths. And so then substituting in what we know for a, then we can now solve for b. So we can just go ahead and subtract 8 and 351 thousandths on each side. And so we get b equals negative 1,000th. And then we also know c here, because when s is 0, then d of s is 0. That's just our y-intercept. And so c will be 0. And so then plugging that into our standard quadratic function model, then we would get d of s equals 8 and 351 thousandths s squared minus 1,000th s, and then plus 0, we don't need to put that. And so now we have our two function models, one a quadratic and one a linear. And so now to answer the rest of their question about the RV stopping at a speed of 55 miles per hour, wanting to know where it stops, d of s, then we first need to know what s would be. And so remember that s is equal to the speed, in that case would be 55 divided by 10. So 55 divided by 10 is just 5 and 5/10. And so we need to plug that into both functions and compare them. And so first in our average rate of change function, plugging in 5 and 5/10 into our function, then we get 321 and 475 thousandths. And remember that's in feet. And so then we'll do the same plugging into our other function. And so here we get 252.61225. And so to check for reasonableness with these two stopping distances, let's go ahead and check and see where it should be on the table. And so for 55 miles per hour, that should come right in the middle between 50 and 60. And so it should be somewhere in the middle between 208 and 76 hundredths and 362 hundredths. And so our average rate of change function gave us 321, a little bit more than that. And so that's not reasonable really, considering that it should be between these two numbers. We have a range of values there. But our quadratic function actually 252, a little bit more than that, that actually does fall right in between those two values. And so that would be a reasonable solution. And so we can see here that our quadratic function model is more accurate. So now that we've gone ahead and answered these questions, let's go ahead and summarize. Using average rate of change, d of s equals 58 and 45 hundredths s for s is greater than or equal to 0. There is no second linear function generated using average rate of change since the data are increasing for all the values in the table. Using finite differences, d of s equals 8 and 351 thousandths s squared minus 1,000th s. The stopping distance of an RV driving 55 miles per hour, s equals 55 divided by 10 equals 5 and 5/10. Using the function model generated by average rate of change to predict the stopping distance in feet for an RV driving 55 miles per hour, d of 5 and 5/10 equals 321 and 475 thousandths feet. Using the modeling function generated by finite differences, d of 5 and 5/10 equals 252.61225 feet. Since 55 miles per hour is between 50 miles per hour and 60 miles per hour, it makes sense in this situation that the stopping distance of an RV driving 55 miles per hour would be between 208 and 76 hundredths feet and 362 hundredths feet. The function model generated using average rate of change predicted a stopping distance of approximately 321 feet. This is not a reasonable prediction since it is not between 208 and 76 hundredths feet and 362 hundredths feet. The function model generated using finite differences predicted a stopping distance of approximately 253 feet. This is a reasonable prediction since 208 and 76 hundredths is less than 253 is less than 362 hundredths.